For our last lecture video talking about the physics of sound waves, we're going to get into what happens when waves can occupy the same space at the same time. This part of physics is known as wave interference. Now, to get into wave interference, it's useful to start with an example that we can see the wave. You've probably experienced ripples in a pond or ripples on the surface of water before. Well, if you have more than one source of the ripples, those ripples are propagating outward from their source, and they are going to interact with each other. If you've seen those ripples interact, they don't just stop being a ripple altogether because they smacked into another one. They don't necessarily bounce back to their source either. Instead, they pass through each other. And when they pass by, they continue on unchanged. That these ripples just continue going. Now, there are a couple different types of interference. What happens when they're occupying the exact same space at the exact same time? When they add together to produce a larger amplitude, so both pulses are on the top, essentially, we get what we call constructive interference, like constructing a building. If they interact and negatively kind of cancel each other out, that's what we call destructive interference. So those they kind of make sense if you think about what the words mean. Well, we can mathematically talk about their amplitudes as well. For constructive interference, if you have a wave pulse of amplitude 1 and a wave pulse of amplitude 2 heading towards each other, at a certain point they get to the middle, and as they're occupying the same space at the same time, those amplitudes add up to give you an amplitude of 3. Likewise, if you have 1 and 1, that gives you an amplitude of 2. And if you have 3 and 1, they add together and give you an amplitude of 4. Okay, so that's pretty simple, pretty straightforward. Destructive interference is a very similar thing. That if you have an amplitude of positive 2 and an amplitude of negative 1, they cancel each other out a little bit, but not all the way. You end up with an amplitude of positive 1 amplitude. If you have an amplitude of positive 1, or amplitude of positive 2, amplitude of negative 3, you get an amplitude of negative 1. And then finally, if you have an amplitude of positive 1, amplitude of negative 3, what's your final amplitude? Well, it's as simple as the other ones. You end up with a negative 2 sort of amplitude. They cancel each other out with subtraction. Now, that was a very simple example, looking at single wave pulses. But you can have multiple waves that are happening at the exact same time. Actually, most sounds that we hear are combinations of waves. My voice right now isn't a pure bell tone at one frequency, even if I'm singing a note. There are other frequencies that are happening. So if you add up those different waves that are occurring at the same time, you get what's known as a superposition of waves. And the math behind that is you're just adding up points along the way. So if I start out here, I start with 2 points that are both at 0. Those add up to 0. So I'm going to place a point here in my superposition wave at 0. Next, we have an amplitude of 1, amplitude of 2. Add those together, we result in an amplitude of 3. Next, we have amplitude of positive 2 and 0, adds up to 2. A positive 1 and a negative 2 adds up to a negative 1. And then 0, 0 adds up again to 0. We can continue this all day, but I'll let it kind of run through here, adding up those two waves to get these collections of superpositions down below. We can connect that with a smooth waveform, and this is the wave that would happen if you had wave A and wave B playing at the exact same time. Notice it looks a little funky, but both frequencies are in there. You can see this oscillation of wave B, the frequency that's showing up there, and you can see the general path of wave A as well. In real life, you're having a superposition of many, many waves, not just 2, not just 1. So you get a waveform that looks a little crazy, but it has all of those other frequencies kind of baked into it. An example, a question that's been on an Ivy physics exam in the past is this one here. Both waves below are moving at 0.5 meters per second toward each other. What is the displacement at a distance of 1 meter after 4 seconds has passed? All right, so my first step is I want to figure out where each of these waves are going to be in 4 seconds. If they're moving toward each other at 0.5 meters per second, after 1 second, they go 0.5 meters. After 2 seconds, another 0.5, another 0.5, and then here's where they are exactly 4 seconds later. The question is asking, what is the displacement overall at a distance of 1 meter? Well, a distance of 1 meter is showing up right here. This pink wave is at 3 meters high, +3, and the blue wave is at -2. If I find their superposition, that +3 and that -2 results in a superposition of +1, +1. So again, I figure out where those waves are gonna be, not where they were in the original drawing, and then figure out how do they interfere with each other to result in an overall. I can also look at this in terms of a pretty neat application. You may have heard of something called a noise canceling headphone. There are 2 different types of noise canceling headphone. The first type, the cheaper, is called a passive noise cancellation. Basically, it's this earmuff that tries to physically block out as much of the sound as possible so that you're only hearing the sound from the speakers inside the headphones, not the airplane that's whirring around you. Well, the other type is something called an active noise cancellation. In an active noise cancellation, there's actually a microphone in there that senses the sound that's around you, the ambient noise, and then shifts the wave and sends in a second wave pulse, a second sound signal on top of the music that you're trying to listen to. This shifted wave is exactly 1/2 of a wavelength away from what it was. It's shifted that amount of the phase, and it's the same thing as adding up in this picture here these 2 longitudinal waveforms, that when they add together, those compressions and rarefactions cancel each other out and give you just this uniform pressure. So you can totally cancel out a sound in this way by actually adding a sound signal in just the right way to the signal that you're trying to cancel out. We can look at the same sort of thing in a couple of different ways. Here is an IB question that's looking at that idea of cancellation in terms of a transverse sort of wave rather than longitudinal. 2 wave pulses travel along a string toward each other. The diagram shows their positions as moment in time. Which of the following shows a possible configuration of the pulses at a later time? According to this picture here, is it A, B, C, or D? Well, at some point down the way, these 2 wave pulses will occupy the same space at the same time. Since they have the same amplitude, just flipped, they are going to cancel each other out entirely and give you C. For a split second, there will look like there's no wave at all. And then, of course, a split second later, they will continue on unchanged. That this one will still be on the bottom. It will just be on the left side. Then the one on the top will be on the right. So if you have more than one source, you can actually have these multiple sources interfere. If you are sitting perfectly apart from 2 speakers that you're the same distance, and you experience the compressions at the same time, the rarefactions at the same time, or crest trough at the same time, those amplify each other, that you're experiencing constructive interference. It's also possible, though, that you can have one speaker slightly out of phase from another speaker because you're not the same distance from each of them, which means that you experience one speaker's sound as a compression at the same time that you experience a rarefaction from the other, and those cancel each other out. In the same way that we saw those dots cancel each other out with the sliding transparencies, that gives you destructive interference. So I want to show you a couple other examples of this and how we can actually turn this into a numerical, mathematical relationship. Say I have 2 speakers that are both exactly in the same place. If they are at exactly the same space and they have a wavelength of lambda, we say that their path difference is 0 lambda. They start in the same place. There's no difference there. In this case, you're experiencing crest with crest, rarefaction, compression. That is a constructive wave. But if I shift one of those speakers by half of a wavelength, so it's half of a wavelength closer to you than the other one, notice how those waveforms cancel each other out. that at a phase difference of 0.5 lambda, half of that wavelength, we end up with a destructive wave. If I continue to shift it so that it's a full wavelength away, now we're constructive again. The compressions happen together. That's constructive. Shift it again another half a wave, so we're at 1.5 wavelengths. That's destructive. You can see that they cancel out. Shift it further, 2 wavelengths exactly. That's constructive. And then finally, 2.5 wavelengths, you guessed it, is destructive. So we see this pattern here that all of our constructive are 0, 1, 2. They are exactly integers of that wavelength. We would call that a path difference of n times the wavelength. An integer times the wavelength. Destructive is all 0.5, 1.5, 2.5. They are an integer plus a half of the wavelength. So we would call that n plus half times lambda. N is any integer. So notice that if it was 2, if n was 2, you would have 2 lambda or 2.5 lambda respectively. These are known as coherent waves because they have the same frequency and a constant phase difference, that they're not changing in their phase difference as the sounds are being played. I also want to note here that these aren't the only 2 path differences that you could have. Obviously, there are lots of places in between where I stopped that speaker. And in that case, you're going to have a somewhat constructive and somewhat destructive wave. So you'll have somewhere in between those. These are the 2 that we care about calculating because they're our maximum and our minimum. So it kind of gives you that threshold. This is given to you in the data booklet, and without going through that derivation or seeing where it comes from, this is one of the most confusing equations on here, and we're going to use it in a slightly different way. So if you need to go back and re-watch that animation, I think that's a helpful one, but let's see how this is used in practice. So let's have a speaker play some pulse here. That has a wavelength. Let's say this sound, this frequency has a wavelength of 0.6 meters. That's the length from rarefaction to rarefaction, this low pressure zone. It's also the length from the compression to compression, the high pressure. All right, now let's say that I have another speaker playing a coherent wave at another distance on the other side. And I place myself right here, not exactly in the middle, somewhere offset so that I'm 2.1 meters from one speaker and 1.8 meters from the other. And again, these are playing exactly the same wave at exactly this wavelength. I can figure out the path difference here. The path difference is just the difference in distance that I am from the 2. Notice here, they're not going the same direction, but the path difference is calculated the same way. It's 2.1 now minus 1.8 to give me a path difference of 0.3. As a reminder, these are the 2 equations that are in the data booklet. Constructive would be a path difference of an integer number of wavelengths, and a destructive would be a path difference of an integer plus half number of wavelengths. So we need to know, is this an integer or is this an integer plus half? Well, this is the general form, as path difference is equal to something times the wavelength. Well, I know the wavelength and I know the path difference, so let's plug that in. 0.3, that path difference, is equal to something times 0.6. Well, you can rearrange and solve for whatever that something would be. In this case, the only number that fits there is 0.5. 0.5 fits this destructive path difference. That's 0 plus half, which would be a destructive interference. So if I play these waves, we should see a destructive zone right here at this point. All right, when they connect, notice that here, if I pause it at this instant, I see that these waves are canceling each other out, giving me a consistent pressure zone that isn't just a rarefaction or compression. It's evened out, so it's destructive. All right, let's look at another example and what it would look like to find a maximum here. So I'm going to start with that same initial sound wave. This initial sound wave has a wavelength of 0.6 again, and now I'm just going to space them slightly differently. So now I am here with 2.1 meters from the first speaker, 1.5 from the second. So that path difference is 0.6 meters. Again, my constructive is n times wavelength. Destructive is n plus half times wavelength. So if I take this generalized form, the path difference is something times the wavelength. Well, that path difference was 0.6. The wavelength is 0.6. So this something is just 1. That is a perfect integer, so we would consider that constructive. If I play that wave, we should see them constructively interfering to give you an even larger sound, a higher amplitude, louder sound there at this point, versus the other one. If you were at that point, you would hear essentially nothing. All right, another way that we can draw this is something called a wavefront diagram. That these wavefronts are represented by these lines. Those lines you can consider the compressions of the waves. And the space in between is where the rarefaction would be, the low pressure zone. So two coherent point sources, S1 and S2, emit spherical waves. We're going to draw them as two-dimensional because it's hard to draw the sphere. Which of the following best describes the intensity at points P and Q? Well, if you look at point P here, it lands right on the line propagating from S1 and S2. So that would mean you're experiencing the compression of each of them at exactly the same time. That would be a maximum. Here, Q is right on the line for one of them and halfway in between for the other. So you're experiencing one compression and one rarefaction. That would give you a minimum. So IB likes to ask in this format sometimes where it gives you a table and says which row of the table is right. Well, in this case, the one that's right is P is a maximum, Q is a minimum, so that would be A. Another example that you might see is a situation here where you're not given the wavelength, but instead you're given other properties of the wave. So two speakers are separated by a distance of 5 meters. If they emit a coherent sound signal at 850 hertz, and the speed of sound is 340, is the person standing in a maximum or a minimum location? We're going to assume that they have one ear. In this case, that's exactly 2.1 meters from one speaker and 2.9 from the other, which means that they have a path difference from those speakers of 0.8. That's the same thing that we did before. The thing that's a little bit different is instead of giving you a wavelength, we're giving you here a frequency and a velocity, a wave speed. Well, we can find a wavelength from that using the wave speed equation. That's 340 divided by 850, the frequency in hertz, gives me a wavelength of 0.4 meters. 0.4 meters is my wavelength. 0.8 is my path difference. This is my generalized formula to help me figure out if it's a maximum or a minimum. If this is an integer, we know it's a maximum, and it is. 0.8, the path difference, divided by 0.4 would give me 2. Since that is a perfect integer, we know that that would be a maximum there. So they would definitely hear some sound. They would hear it amplified in constructive interference. In another example here, let's say that you are not standing perfectly in between. You're going to be experiencing one from an angle here. So if you're standing directly in front of one of the speakers are 4 meters apart, and you are 3 meters from that speaker, that means with a 3, 4, 5 triangle that you're 5 meters from the other. That's just the hypotenuse of this right triangle, which can help you find the path difference. In this case, isn't 1. Let's change that right now. All right, that's better. Your path difference is 2. 5 minus 3 is 2 meters. So now we need to find the wavelength. Our speakers are playing a frequency of 680 hertz. Go ahead and find the wavelength and then figure out, is that at a maximum or a minimum location? As a hint here, you can find the wavelength using this equation. Velocity, the wave speed divided by the frequency. So 340 divided by 680. That gives you a wavelength of 0.5. And then your path difference is going to tell you here if this is an integer or an integer plus half. So go ahead and figure out from that, would that give you a maximum or a minimum? 2 meters is our path difference. 0.5 is our wavelength. 2 divided by 0.5 gives you 4. That is going to be a maximum because it results in a perfect integer. Well, the follow-up question then is what frequency would result in the exact opposite effect? If I was still standing exactly here, is there a frequency that would destructively interfere? Well, if you think about it, all that I need here is a wavelength that would result in something that is, ends in 0.5, some integer plus half. And I could choose anything here. I could choose 0.5, I could choose 1.5, 2.5. Since I started with 4 here, I want a frequency similar, I guess. I'll say 4.5. But anything with 0.5, as long as that relationship is going to give me exactly half a wavelength away in our path difference. If I solve for my frequency, my wavelength here, this wavelength is going to be 0.44. And if I want to go backwards, figure out with my speed of sound, 340 meters per second, what my frequency is, I can find the frequency is just the wave speed divided by the wavelength, and that's 773 hertz. So, frequency of 680, that's totally fine, but a frequency of 773, that would result in a minimum from these two locations. So the main takeaways here in this video, you should be able to qualitatively and quantitatively interpret cases of constructive and destructive interference. And it's really nice to be able to draw some sort of diagram representing what that looks like. You should be able to add up two waves with superposition to create some new waveform, like we did with all of those points to create that funny looking wave. That was a combination of the two. And you should be able to use wavelength and source distance to identify, is it a maximum or is it a minimum location based on that path difference and wavelength.